Next slide. Well, good afternoon. This is already 12:22. We're supposed to start a class at 12:15. I waited around to see if anyone else was going to show up, but so far no one has. Hopefully others will be coming in later. Before I get going today, let me explain a few things about some changes, office hours. Some of these are just for this week, or maybe a little bit beyond this week, and others will be permanent for the rest of the term. Okay, first and foremost, we say this, we are in the second half of the term now. Midterm was sometime over the weekend, so we finished the first mini-term last week, starting second mini-term this week, and part of that is the reason for some of my office hour changes. Not all, but part. Okay, now, while I'm on that, let me hit this other issue. Sometime in this week, they're going to open, usually they open for us to do midterm progress reports. So that means anyone who doesn't have an A or B at midterm, we're supposed to report the fact to administration, and then someone will try to get in touch with you, see if you need help with tutoring or counseling or other things like that. Okay, from this class I've received 2 papers and 4 tests, test 1. Now among all those that leaves 1 person, but I'm not sure that person's still in the class, so maybe this is not an issue then, because this person hasn't been in the class for a while, and it seemed like they were in class, out of class, in class, out of class. I don't know what the final decision was, so I don't know if he's still in class. But if you're still listening, I need either a research paper or a test in test 1 in this week, if possible. All right, that said, let's go back to my office hours. Well, since the second mini-term, first mini-term on Tuesdays and Thursday afternoons, I had a physical science class that went from 1:15 till 5:45. Second mini-term, I have physical science 2, but it doesn't start at the same time because several of the automotive students, some of them have to take that course, and they don't get out of their block class until 3 o'clock, which means we can't start until 3:15. So that means that class will be going from 3:15 till 7:45. Well, the good news of that is that my office hours are longer now. Tuesday and Thursday, they'll normally be from 11:15 till 3:15 rather than 11:15 to 1:15 that they were for the first mini-term. So that doubles the office hours on Tuesdays and Thursdays. That's the good news, both for you and for me, because I'll be in the office more and I'll be able to get more things done, and you can come see me. Opens up more time for that. The bad news is I'm here till 7:45 on Tuesday and Thursday evenings, which is going to be pretty late. So I probably won't leave before 8 and get home 8:45-ish. That's going to be pretty late. So anyway, but that's what it is. All right, so there's that. Okay, it's number 1. All right. The next change of office, and that's for the rest of the term. The next change of office hours is because I have a doctor's appointment tomorrow. So this only affects classes this week and early next week, okay? My doctor's appointment is from is at 10:40 tomorrow, which means I have to be at the lab at 9:40 for labs, which means I have to leave campus by 9 o'clock, which means by 8:30 class we'll only have a half hour of class. So what we've decided to do was start at 8:15 tomorrow, so I'll be there from 8:15. So that does shorten my office hours in the morning. Normally it was 8 to 8:30, now it's 8 to 8:15, and that'll be for this Tuesday, this Thursday, and next Tuesday. I'll be starting at 8:15 rather than 8:30, so my office hours will be shorter on those 3 days. And that makes up the 45 minutes I would have missed. 15 minutes those 3 days will make up the 45 minutes that I would have to end the class early because I have to leave. Now, the other way my office hours are changed on Tuesday is that because my appointment isn't until 10:40, There's no way in the world, I don't think I'll be out of there before 11 o'clock. Okay, if I can even make 11. I doubt if I can, but I doubt if I'll be any before. So that means coming back to campus, it's going to be probably the earliest I'll get back is 11:45. Normally, office hours start at 11:15. They won't. Obviously, will not. 11:45 would be the earliest, but it could be later than that, so it could be 12 o'clock or even later. But they'll go till 3:15. Whenever I get back until 3:15 will be the office hours. Now, I told you how I was adjusting the 8:30 class. Well, the 10 o'clock class is wiped out completely because I have to be there. I have to leave here by 9 to get there by 9:40 to have my labs done, to be for the appointment at 10:40, which goes until probably at least 11. So my 10 o'clock class is completely wiped out. So what we're going to do with that is make up that class this coming Friday. That will be from 9 until 10:15. This coming Friday, we'll make up that class. So my office hours are normally on Friday on the Birmingham campus. This Friday, they'll be on this campus from 8 to 9, and then from 10:15 until noonish or so. So that's the other change. So my Tuesday, Thursday, and next Tuesday morning, office hours are only 8 to 8:15 because I'll be starting that class early Tuesday, Thursday, and next Tuesday. And then Friday, I'll be on Bessemer campus rather than Birmingham campus and making up that class. Okay. After Tuesday of next week, we'll be back to normal, 11:45 till 11:15 till 3:15 for office hours on Tuesday, Thursday. My Monday, Wednesday office hours stay the same. Nothing changes there. And except for this coming Friday, my Friday office hours will stay the same. Okay. I hope that's all the announcements. All right, moving on to where we left off last time, limit of a function of two variables. Hopefully you'll see the parallel in these definitions and the ones you saw for single variable calculus. So let's just go over this quickly. If f is a function of two variables and defined for those two variables for every value except possibly at the point x0, y0. Those are your two independent variables. So x equal x0, y equal y0. At that point, the function doesn't have to be defined. It may be going to infinity or something there. We don't care. Just every place else it needs to be defined. On an open disk, centered at that x0, y0. Okay, that point where it may or may not be defined. Okay, and let L be a real number. Then the limit as xy, the ordered pair xy, approaches that x0, y0 of that f of x, that function, is that value L if for each epsilon greater than 0, there corresponds some delta greater than 0, such that the absolute value between the f of xy and L, okay, is less than epsilon whenever the 0 is less than the square root of x minus x0 squared plus y minus y0 squared, and that entity is less than your delta. Okay? Now, just a little bit of a review of what we're talking about there. Your epsilon measures the difference on the y-axis between the function value and the limit, and if you can make that arbitrarily small for any epsilon greater than 0, then the absolute value means the difference between those for any value epsilon greater than 0. No matter how tiny it is, you can come up with a delta, and that would be when the delta is less than the distance between the xy value and the x0, y0 point that you're interested in. That's what that is telling you there. That's a difference formula, that's square root, difference between x minus x0 squared plus y minus y0 squared. That's the distance between the x, y variable point and the x0, y0 fixed point. If that, whenever you get a delta, that the distance is less than that delta, that guarantees your function is within that epsilon of your limit. Okay? Hopefully that makes sense. It's a lot of blah, blah, blah. Now, graphically, what's that saying? The definition of limit of function with two variables implies that for any point xy not equal to x0, y0, okay? And let me get my pen. I'll try not to mark on it, but just to give you an idea. Here's your point xy. It can be anywhere on that disk that surrounds x0, y0, okay? And that radius of that disk is delta. So the xy, they call it x1, y1 here. Is any point xy within that disk. The distance between that is being less than delta. That's what that's showing there. It can be any point there inside that disk. Okay. Then you guarantee that the function up here, the limit, the function value will be within epsilon of the limit of that function. Okay, the limit of the function will be within the epsilon of the value of that function at that point. So if your function is this sheet that comes down here like that, and you're anything where within that circle of your domain, anything within delta of that point x0, y0, then you go up here, you're guaranteed that you're going to be within epsilon of that limit L. Now, graphically, is this really all that helpful? The L, in my mind, is this value at x0, y0. This value here, that's your alpha of xy. So that's the one up here. The way they drew it, it made it look like that's where L is, and that the other is within epsilon of that. But because this is a three-dimensional drawing on a two-dimensional space, it's hard to tell. But this, as you see here, this cylindrical shape here that you see here is between you and the YZ plane. So it's shadowed, you might say. It's moved forward some. So this indeed will be that point, and the function value will be somewhere up here within epsilon of that limit. Okay? Now again, I don't know if the figure helps any, but that's what it's telling you. You can get that epsilon as small as you want, however small you want, if you can always find the delta such that those conditions are met. You've shown the limit exists. Okay? So the definition of limit of two variables is similar to that of the limit for a single variable, yet there is a critical difference. To determine whether a function of a single variable has a limit, you need only test the approach from two directions, right and left. That's the only way you can go on a number line. Okay? When the function approaches the same limit from the right and the left, you can conclude that the limit exists when you're single variable calculus, okay? However, for a function of two variables, the statement that xy approaches x0, y0 means that the point xy is allowed to approach x0, y0 from any direction it wants. And if the value of the limit as xy approaches xy x0 as alpha of x is not the same for all possible approaches or paths to the x0, y0, then the limit does not exist. Okay? Now that seems a little bizarre, but it is indeed true. Now, let's go back to this figure. It looks like here that would be good, because wherever the function is on that, you can approach this value here any way you want to, and it's still going to have that same limit. Okay? There are other cases where approaching from a different direction, different axis, different approach may give you a different value, then the limit wouldn't exist. Okay. Now, this is one of those duh kind of problems to me. The limit as xy approaches AB of the value x. Okay, for the life of me, I don't know what their point here is, but if x is approaching A, x is equal to A. I mean, goodness gracious, how could you get anything else? Okay, the limit as xy approaches AB, obviously the x is approaching A, so the limit of x would be A. Okay, now it says verifying that by its definition. Let's just see how they do it. I just don't want to get into it. So let's let f of xy equal x. That's exactly what your function is there. Your L here is your A. That's the limit. You need to show that for any epsilon greater than 0, there exists a delta neighborhood around AB, okay, such that the absolute value of f of xy minus L is equal to the difference in those two is equal to the distance in those two. So basically, when you do this minus this, you're also doing this minus that, because those are equal, these are equal. So the difference between these two would have to be the same as the difference between those two, and that's going to be that difference between the x and the A. That's going to be your delta. That's the delta neighborhood. And then you can just, for any epsilon, choose a delta less than that. That's all you do. Whenever xy is not equal to AB, it lies in that neighborhood. Okay. Now, this is just saying, let's go back to here. There's your F, that's the X, that's the L and the A, okay. These are just all true statements, and I don't see why in particular one follows the other. They're both true because of what we said before. These statements here lead to be that one, and that's exactly what this statement here is. These two are equal, okay? Irregardless of what this one is, the others have to be true, but for any x and y close to AB, they will be that. Okay, now, erase this. The absolute value of x minus a is the same as the square root of x minus a squared. Okay? Square root undoes the square, so x minus a would be what you would have under there. Within a sign, you know, plus or minus. It could be the a is greater than x, so then that would be a negative under there. That was fine because you squared it. And that has to be less than or equal to the sum of x minus a squared plus y minus b squared. So I'm sure there'll be that's got, okay. This thing right here, because it's squared, it's got to be positive. So therefore you add something, the least it can be is 0. And if it's 0, then it's equal to the thing above. If it's anything positive, then it'll be greater than the thing above. So that's an obvious fact there. Okay? So let that be our delta. Whatever that thing is there, actually let it be less than delta. Choose a delta, any delta value a little bit more than that. So here we chose delta equal epsilon, and the limit is verified. The limits of functions of several variables have the same properties regarding sums, differences, products, and quotients as the limits of functions of single variable. That's what I said. All these things are very, very similar. It's not almost being exactly like or exactly corresponding to the functions of a single variable. Okay. I'm going to need to take a pause here. Sorry about this. But I crammed down a little bit of lunch, I think too fast, and my head's giving me fits right now. So I think I need to go. I ate and didn't have time to do any drinking of anything. So I'm overly dry, and I think that's what's creating the head and also eye problems that I'm having. So I'm going to put this on pause, and I'll be back in just a couple of minutes. I did want to turn the page, and I just now realized they skipped example 2 and 3. This figure we see here is next to example 4. So let me go back to too far. Okay. I almost feel dizzy. So, all right. Sorry, I should never have gone out into the hall. I got, stopped on my way to my office by a student who needed to turn in a take-home test. She had to go get it and stuff like this, so that held me up a little bit. Got to the office, got something to drink. And then on the way back, got stopped by an instructor who has a mini-term class that we needed to do some adjusting to the schedule. So it's crazy. So that's why I'm so late getting back. But anyway, let's go back to where we were. I think this was the end of example 1. And I think we got that pretty much covered. Yeah, I don't know why this went back to this. Oh, I think I know. I was going to do example 2. And example 2 wasn't in the text, right? Right. Okay, 2 and 3. So that's what I was doing. Back. Okay. Let's see if we can get example 2 in here. Find the limit as xy approaches 1, 2, of 5x squared y over x squared plus y squared. Okay? Now, I don't know if you remember from single variable limits that we were doing. First thing you usually try is plug it in, plug it in. Before we do that, though, let's just make sure that we don't have any problems here, okay? And most of the time in this a circumstance like this irrational expression, the numerator isn't going to ever hurt you at all unless you had a square root in it or a log in it or something like that. But this is just a polynomial, mixed polynomial, but it's a polynomial in the numerator, okay? It's the denominator we have to worry about. Well, guess what? X squared plus y squared will never be 0 unless x and y are both 0 at the same time. Well, we're not going anywhere close to 0. We're getting x is approaching 1 and y is approaching 2. So x, y is approaching the point 1, 2. No zeros involved in either one of those, so there's certainly not going to be an issue with 0 in the denominator. So all we have to do here, plug it in, plug it in. So that would be 5 times 1 squared times 2 x squared y over 1 squared plus 2 squared. And that would be 10 over 5 equal 2. That limit is going to be 2. So it does exist, and it exists at 2. Now, let's do example 3. I don't think it'll be quite that simple. Okay? Find the limit as xy approaches 0, 0 of 5x squared y over x squared plus y squared. Well, look here, that's a 0 over 0. That is an indeterminate form. Okay? So you cannot determine existence or non-existence of a limit by taking the limits of the numerator and the denominator separately and then dividing. Now, what you have to almost do is the graph. And thank goodness I'm not going to have to draw that graph. You see it in the text there. Okay? And if you look at it in the text, that is one bizarre looking thing, and it's a three-dimensional figure drawn in 2 dimensions. They've done their best to shade it so you can kind of figure out which way it's going. But and just looking at that, the figure, it appears to be going towards 0. Okay? And that's all you can really say about it. And I wish they had this drawn in the slide set, but I'm hoping you all have books and you can look at it. You can see you have one thing. If the function was coming in the y-axis from the negative end, that would be approaching 0. The y-axis from the positive end approaching 0. And then there appears to be a line coming from approximately it's not the bisecting line, but a line coming down toward the origin, and then one coming up that appears to both be approaching 0. So it looks like whatever path you choose, you are approaching 0, 0. Okay? So that the value would be 0 there. Okay? Now, this is a hairy I want to say proof almost, but it's not quite a proof. It's just working the thing out. And, you know, the first thing they notice in the solution, I guess you would say, is the absolute value of y is less than or equal to x squared, square root of x squared plus y squared. Okay, now that's the case, because square root of the absolute value of y would be the square root of y squared. Okay, that basically is definition. So if you add something to y squared, even if it's 0, then the absolute value of y will be less than or equal, if the x happens to be 0, x squared root of x squared plus y 0. X squared plus y squared. Okay. So with that the case, and then it also says that x over x squared over x squared plus y squared also must be less than or equal to 1. And why is that? Well, you've added something to x squared in the denominator, a positive number, or at most 0, and then you'd be equal to x squared over x squared would be 1. But if anything larger than 0 that you add to the denominator is going to make the denominator larger than the numerator, which means that expression will be less than 1. Okay? So, there's 2. Okay, then in a delta neighborhood around 0, 0, you have 0 less than x squared plus y squared less than delta. Okay? Follows that for the xy not equal to 0, 0, okay, the absolute value of xy minus 0 would be the absolute value of your f of xy is 5x squared y over x squared plus y squared. So, and subtract 0 from you. So that's exactly, I mean, that's just a pretty obvious statement there. And that's equal to 5 times the absolute value of y, which is less than square root of x squared plus y squared. Okay, sorry. What they did, yeah, okay. I haven't written down the rest of this, but I will write down this line. Okay, this, by the way, is your f of xy. Okay, so the absolute value of f of xy minus 0 is equal to the absolute value of 5x squared y over x squared plus y squared. Gotta be, because you subtract 0 from it and you've got the same thing. So that's the same thing. Now, if you pull the y out, especially the absolute value of y, then you have absolute value of y times 5x squared over x squared plus y squared. Okay? I'm sorry, they pulled the 5 out as well. 5y over that. Okay? Now, as they just talked about, this part right here has to be less than or equal to 1. Okay? And earlier they said this is less than or equal to x squared plus y squared. So this will be 5 times the absolute value of x squared plus y squared, square root of that, sorry. Okay? And this is less than or equal to 1. Okay? So this will be, let me get my symbols right. Okay, less than or equal to. Okay? Now, that right here is your delta. Okay? So this is less than or equal to 5 delta. Okay? Now, if that difference there is less than or equal to epsilon, then the epsilon, or delta, just choose a delta, epsilon over 5. Okay? Choose a delta equal epsilon over 5. And then you're guaranteed for that to happen. So no matter how small you choose your epsilon, however close you're going to allow yourself to get to that value, just you can guarantee you'll get there if you choose an epsilon, a delta, less than or equal to 1/5 of that. whatever value epsilon you choose. Now, for some functions, it's easy to recognize the limit does not exist, and that, I think, is leading to okay. Oops, yeah. This one. For some functions, it's easy to recognize that the limit does not exist. For instance, it's clear that the limit is xy approaches 0, 0 of 1 over x squared plus y squared can not ever exist, because that's not an indeterminate form. That's 1 over 0, which is an undefined form. Undefined is never going to happen. Okay? And here's the picture of what's happening there. As xy approaches 0, f of xy, which is what that function is there, is going to infinity faster and faster and faster as xy approaches 0, 0. So there's no way you're going to get any bounding in there at all. Okay? No matter what path you take or anything else, it's going to go to infinity. Okay? That limit doesn't exist, and you can basically look at it and see that's a 1 over 0 form. The only ones that have a chance of existing are either those when you plug them in, they give you a number, or when you plug them in, they give you an indeterminate form, which would be 0 over 0. But something like this, a 1 over 0, no, undefined form, never going to happen. Okay. Now, they are skipping example 4 as well. Okay, so let's go back and do example 4 here. And this, by the way, is at larsoncalculus.com. You can see an interactive version of this type of an example. I don't know if this one exactly, but something pretty close to it. And by the way, larsoncalculus.com, you don't need a passcode. You don't need anything. It's a free website. Anyone in the world, someone who's not taking this course, could go to that website and look at see what it's talking about. They may not understand it, but they could do it. So you're certainly welcome to do it. And what you're asked to do here in this example 4 is show that this limit does not exist. Now, I wish they hadn't told you that already. That the limit as xy approaches 0, 0, I can't write, okay, all right, let me try that one more time. Okay. Goodness, my eyes are drying out again. Hard to see. The limit is xy approaches 0, 0 of x squared minus y squared over x squared plus y squared squared. That limit does not exist. Okay. Well, first thing to do is look and see what happens you plug it in. You get 0 over 0 indeterminate form. Okay? That's all. Can't say one way or another whether it does or does not exist because it's indeterminate. Now, their first step is to set this equal to your f of xy, which of course that's what we think, and that would make perfect sense. Okay? Now, as xy is approaching 0, 0. Okay? Let's take the x going to 0, but the y going to 0 a lot more slowly. Okay? Here's a couple of ideas or thoughts to just sort of get a conceptual feel for this. Okay? Now, let's imagine that y is a little bit greater than x, like maybe twice x. Okay? Then your numerator would be x squared, but the xy is approaching 0, so, but just the x is, the y is, several times larger. So let's say 3 times x. Okay. Now, if you put in say, just for instance, y is equal to 2, I said 3, so 3x. So x squared would be x squared, and y squared would be 9x squared. Okay? So in the numerator, you have x squared minus 9x squared and x squared plus y squared would be x squared plus 9y squared, 9x squared. That would be 10x squared. Okay? And the ratio of those two would be a negative 9x squared to 10x squared. That would be negative 9/10. All right. Goodness, I can't read my writing. That's negative 9/10. Okay? Now, that would be if you were approaching that, the x and y are still approaching 0, but that would be coming in at the value would be negative 9/10 of that shape. Now, you can come in a different way, where say x is 1/3 x, if you reverse those and said x is equal to 3y, both could be approaching 0, and then you would have 8y squared over 10y squared, and that would be a ratio of 4 to 5. Okay? So that would be approaching a different limit if you came in from a different direction. Okay? And that obviously is not going to be, that limit can't exist if it's having different directions values from different directions. Okay. They did sort of the same thing. They chose it coming in from if you came in the x-axis where y is 0, you get x squared over x squared is 1. When you come in the y-axis where x is equal to negative x, then you run into serious sorry, my throat's going on me. As you're coming in the y-axis, the x-axis where y is equal to 0, the limit is 1. If you come in the y-axis where x is equal to 0, the limit is 0. You can't have a 1 and a 0 coming, so that limit doesn't exist. Okay. The ones I gave were also true, just a little more calculation to them. Okay. Oh, I went backwards to graph. Okay. So let's pick up on continuity. And I'm sorry, I need to go clear my head again, so I'll try to get back just as soon as possible. I hope this time no one stops me in the hall. Let me see, before I do this, what kind of time I have. Yeah. Sorry, I wish I could go 30 more minutes without having to pause, but I don't think I'm going to make it. So, all right, this time was more successful. I did see 3 people who stopped to speak, but that was only just to say hi, so I was able to keep walking. So, anyway, let's move on to page 888. Continuity of functions of 2 variables. Okay, now this follows from, that's why we had to do the limits first. The limit of f of xy, which is 5x squared y divided by x squared plus y squared, we had in both of the last 2 examples. First, as the xy approaches 1, 2, can be evaluated by direct substitution. Why is that? Because it's continuous at that point. Okay, so there's no way that as xy approaches 1, 2, everything there is defined, continuous, smooth, everything is perfectly fine. And that limit was 2. In such cases, the function f is said to be continuous at that point. However, the other one at 0, 0, that same function, was not continuous because it wasn't even defined there. Well, yeah, it wasn't defined because the limit did not exist there. It was some limit coming from one direction, some from another direction, so the limit does not exist. Okay? So therefore it was discontinuous at the point 0, 0. Same function, but there. So here's your definition of continuity of a function of 2 variables. Function f of 2 variables is continuous at the point x0, y0 in some open region R if f of x0, y0 is defined, okay, one thing, and is equal to its limit of f of x as y approaches x0, y0. So it's basically the same thing as before if it's defined and the limits are the same. That is, the limit of xy approaches x0, y0 of f of xy is f of x0, y0. Okay? Now, I don't know why that vertical bar is there. It's not in the book. There's no reason for it to be there. It just somehow showed up. Okay? The typesetter on the slides just messed up, put in something there. Maybe put in absolute value, took one of them off and left the other one in. They didn't need them in there, so you shouldn't have them in there. Couldn't have them in there. Now, see, both conditions are met here. The limit does exist, and so one thing, it has a value there, and that the limit of the value is what you would expect it to be. The function f is continuous on open region R if it's continuous at every point in that open region R. Okay. Now, back in example 3, which is the one when it was approaching, this function was approaching 0, 0, is not continuous at 0, 0 because the limit at that point exists. However, you can remove that discontinuity by defining f at 0, 0 to be equal to its limit there. Such a discontinuity is said to be called a removable discontinuity. The function f of xy of x squared minus y squared, this is the next one we did. What was that, example 5 or something like that? No. Example 3 was the top function there approaching 0, 0. That limit did exist. Okay, sorry, I was saying that wrong. It's the next one. Example 4 is the one that did not exist, and this is the one that does not exist. That function is not continuous at 0, 0. The discontinuity is not removable because it had one value coming in one direction and one in another, different from a different. So it had no value you could have put in there to make it removable because different routes you approach 0 would produce different values. So which one do you choose? None of them are going to be continuous everywhere. Okay, so here's theorem 13.1, sort of the bottom half of page 888. If k is a real number and f of xy and g of xy are continuous functions at x0, y0, then the following functions are also continuous at x0, y0. Certainly the scalar multiple kf or kg, okay? The sum of the difference formulas, f plus f g or f minus g. The product formula, f times g, or of course g times f, okay? The quotient formula, f divided by g, as long as g of x0, y0 is not equal to 0, because then you would be dividing by 0, which you cannot do. This theorem also states the continuity of polynomial and rational functions at every point in their domains. That's the key. I was going to say rational functions wouldn't be at every point, but every point in their domains. If it's not defined somewhere, it's not in the domain. Furthermore, continuity of other types of functions can be extended naturally to form from one or two variables. Okay? Now, these are two figures at the bottom of page 88. For instance, the functions whose graphs are shown in figures 1323, the one on the left, and 1324, the one on the right, are continuous at every point in the plane. Okay? And sort of why is that? Because these surfaces that are formed from these functions are smooth and continuous everywhere. Okay. Well, let me back off. The second one there. At the origin, it makes it, the way they've drawn it, it makes it look like it's not continuous at the origin, but I see no reason for it not to be continuous at the origin. Because y of 0 is 0, of course, and 0 squared is 0, of course, but cosine of 0 is 1. So that part is certainly continuous there. And e to the minus x squared plus y squared, well, as x and y both are approaching 0, x squared plus y squared is 0, or approaching 0. Square root of that is approaching 0. And then negative e of that would be a good function that would be easily e to the minus 0 is approaching 1, okay? Anything, any function to the 0 is approaching 1. So I see no reason for the hole there. It seems like it should come to a point at 1, because cosine of 0 is 1, and e to the minus 0 is 1. So that should be a 1 there, nevertheless, okay? Now, other places it goes positive and negative. E doesn't, but cosine does. Even cosine y squared does. Now, if that square was outside the parentheses, that would not be ever negative, but that one's inside, so it's fine. Y squared, you know, cosine of y squared. That just means you're taking cosines of only positive values, and the cosine goes positive and negative, whereas e only stays positive. Okay. All right. I think we're ready for Theorem 13.2. Continuity of a composite function. If h is continuous at x0, y0, and g is continuous at h of x0, y0, in other words, g is continuous at the value of h that it has at that value, x0, y0, then the composite function given by g composed with f of xy equal g then the composite function g of h of xy, which is g of x of hy, is g composed with h of xy, which is g of x, h of xy, is continuous at 0, 0, x0, y0. That is all right. The limit as x approaches x0, y0, g of h of xy is equal to g of h of y and z of g of h of x0, y0. Sorry, it's hard to talk. Note that in this theorem, h is a function of 2 variables, but g is only a function of 1, because no matter what the x's and y's are, when you operate it on h, you get one and only one solution. To be a function, you would have to be. So that is a single variable solution h for h of xy, and that's what goes in to feed the g function. Okay. Now, it says discuss the continuity of each function. Okay, this is example 5. Okay. Now, f of xy is x minus 2y over x squared plus y squared. Well, numerators don't ever mess with the continuity of something, unless, of course, they have square roots of negative numbers in them, then that would really mess something up, or logs of negative numbers, or logs of zeros, or something like that that doesn't exist. This isn't. This is a polynomial, you know, 2 different variables, but polynomial in the numerator. That's not going to have any continuity issues at all. The only continuity issue here is the x squared plus y squared, and the only place that would be a problem is when x and y are both 0 at the same time. So x0, y0. So the x's and y can both approach 0. Well, what happens in the numerator? If x and y are both going to 0, numerator is going to 0. The denominator is going to 0. So that's an indeterminate form. So hang up. You know, we don't have anything definitive yet. Okay. Now let's think. Is there is that removable? Okay. Okay. Gut feeling is that it would be removable, but I can't. And also the gut feeling is it would be 0, okay? And the reason for that, the denominator, the closer you get to 0, it's getting to be I can tell you right now the second one, g of xy, 2 over x minus y squared, that is 2 over, as xy approaches 0, 0, that's undefined, never going to have, it's not going to be continuous at 0, 0. No way in the world. The top one, not quite as clear to begin with. Oh, that's all you have to say. I'm sorry. It's continuous everywhere except at 0. They didn't ask if there was a, I'm sorry, I misinterpreted the problem. If it was a, when they said discuss the continuity, I was thinking they meant whether it's removable or not. No, they're just saying discuss the continuity, and we said that right at the beginning. It's continuous everywhere except at 0, 0. Not continuous there, and they're not asking whether it's removable or not. It's just not continuous there. Okay. G of xy, it's not defined at 0, 0, and it's not defined also anywhere on the parabola y is equal to x squared, because of that parabola, y minus x squared is equal to 0 as well. So that is undefined, not only at 0, but anywhere on the parabola y is equal to x, 0, x squared. Okay. Yeah, and that's what the figure shows here. 0, 0 certainly is undefined, and that whole parabola, where x equal y squared, that entire surface that you see drawn above there is would not have values. So just exactly like I said, but the picture shows it a little bit better, but then it's a bit on the weird side too. Now, here's the solutions. I didn't know they had the pictures here. Here they are. Because a rational function is continuous at every point in its domain, you conclude that f is continuous at each point on the xy plane except at 0, 0 as shown here. And there's the function. And at 0, 0, one place it's going to positive infinity when x is greater than 2y, and it's going to negative infinity anytime 2y is greater than x. Okay, so that's not removable at all. Okay, it is continuous everywhere except the origin, and it's definitely not continuous nor removable discontinuity at the origin. Okay? In the B part, it's continuous at every point in which the denominator is discontinuous, where it equals 0, and those points are y is equal to x squared, y minus x squared equals 0, so in other words, y is equal to x squared. So you can conclude the function is continuous at all points except those lying on the parabola. And that includes the point 0, 0, by the way. Okay. And that's the picture of it. And it's a continuous function everywhere on the xy plane except on that parabola there. On the outside of the parabola, it's going to negative infinity as you go down. Inside the parabola, it's going to positive infinity as you go down. So, yeah, that's your outside the parabola. Y is greater than equal to x squared. The surface lies below the YZ plane. All right, let's look at continuity as a function of 3 variables. All right. 10 minutes. The definitions of limits and continuity can be extended to functions of 3 variables by considering the points x, y, z within an open sphere, not a circle now on the plane, but a sphere in space, where x minus x0 squared plus y minus y0 squared plus z minus z0 squared has to be less than your diameter of the sphere, which is your delta squared. Now, I have a little bit of problems with them using a delta here, because later when you talk about limits, if they do talk about these, they're going to have a delta which is not necessarily the same delta. So wish they'd have called it something else. The radius of the sphere is called delta, and the sphere is centered at x0, y0, z0, shown here. Now, that point x0, y0, z0 in a region the point x0, y0, z0 in a region R in space is an interior point of R if there exists a delta sphere about x0, y0, z0 that lies entirely in that R. So in other words, if you can draw a little sphere, as small as you want to draw that sphere, and still be inside that region R, that's an interior point. If it's on the boundary, it's not an interior point, it's a boundary point. If every point is an interior point, then R is said to be an open sphere. Okay? The definition, okay, here's the definition of continuity of a function of 3 variables. Function f of 3 variables is continuous at a point x0, y0, z0 in an open region of space R if f of x0, y0, z0, I'll pause just a minute, someone just came in. Okay. Okay. Function of 3 variables continuous at a point x0, y0, z0 in an open region R if f of x0, y0, z0 is defined and is equal to the limit of f of x, y, z as x, y, z approaches x0, y0, z0. So it's basically the same as single variable, 2 variable, 3 variable. That is the limit as x, y, z approaches x0, y0, z0 of f of x, y, z. If that limit, number 1 exists, and number 2 is the value we would expect it to, alpha of x0, y0, z0, then that's a continuous function. Function is continuous in the open interval R if it's continuous at every point in R. Okay. Yeah, let's see if we can do this one. Discuss the continuity of this one. All right. Now, it's not defined, not even just not continuous, not defined at x0, y0, z, at x equals 0, y equals 0, z equals 0. Definitely not even defined there. Moreover, it's not defined when z is equal to x squared plus y squared. So in other words, for every positive number z, that is the square root of a radius. Okay, no, that is a radius. No, the square root of that is a radius, and that sphere whose square root is that z, then you would have all zeros there. Okay, 0 in the denominator there. So obviously that would not be continuous anywhere that's true. Okay, now anywhere that's not true, it should be continuous. Okay. So alpha is continuous everywhere except the points at which the denominator is 0, which are given by that equation. That equation, at each point in space except the points on the paraboloid. By the way, I should have said that it was a paraboloid. Z is equal to x squared plus y squared. Now that's not just an elliptical paraboloid, that is a circular paraboloid. Okay? So everything inside that, outside that, but not on that. Oh, and they didn't even give us a picture of that one. All right, so that finishes 13.2. Homework exercises here, either 3 or 5 or both. They're both at calcchat.com. Worked out solutions are given there, and number 5 is given at calcview.com in more detail. 7 or 9, they're both at CalcChat. Any of the odds 11 through 21, they're all at CalcChat. 15's at CalcView. Any of the odds 25 to 35, they're all at CalcChat. 37's at CalcView. Either 37 or 39. 37's a limit issue. 39's just thinking about it. I would do number 41. And by the way, all those should be at CalcChat. Either 43 or 46. They're both at CalcChat. I'm sorry, 43 or 45. They're both at CalcChat. Do 47 if you can. Okay. And then 49. And both of those should be at CalcChat. Then do any of the odds 51 through 55. They both should be at CalcChat. Either 57 or 59 or both. I'm sorry? Yes, he's been here.
Oh, okay. Well, there's just someone in I guess I'm just real early.
I'm sorry?
No, I guess I'm just real early. I was trying to see if our class had moved today.
Okay. This is a physics class?
Yes.
He's been down in, do you know the lab in 259, the inner lab where that device is set up? Is he taking y'all down there yet?
Mm-hmm.
Okay. If he's not in the classroom now...
Well, there's just like a class there, so I didn't know.
Oh, really?
Yes.
Uh-oh, it may be a second mini-term class. I'm going to have...
They might be out there too, because we don't start. They're not bothering me.
Yeah, okay.
I'm probably bothering you.
All right, sorry about the disruption there. We have a room conflict with the second mini-term class. I think I left off somewhere here. Do either 43 or 45. They're both at calcchat.com. Do 47. It's a limit problem. It should be at CalcChat. Do 49. It should be at CalcChat. Any of the odds 51 to 55, they should all be at CalcChat. 57 or 59, they should both be at CalcChat. 61 through 65, any of those, they should be at CalcChat. 61 is also at CalcView. Do either 67 or 69, they should both be at CalcChat. Any of the odds 71 to 75, they should all be at CalcChat. Do 77, it should be at Calc Chat. There's a true false, 79 and or 81, they should both be at Calc Chat. And then do any of the odds that you choose to do, 83 through either 83 or 85, they should both be at Calc Chat. 83 is just a finding a limit, and 85 is a proof. You don't have to do the proof unless you want to. All right, because I have another class coming in here in just less than 5 minutes, or right around 5 minutes, I think we'll just not get started on 13.3 today and pick up that next time. That's really the meat of the thing. This other is just giving you the background on continuity and existence and all that kind of stuff, limits and that kind. We actually, where the meat of this chapter is, begins with 13.3. So we'll begin that on Wednesday. We'll see you then. So.